Hey, everybody, and welcome to another edition of Probably Private about the problem of memorization in AI and machine learning models. If you've missed some, check out the playlist. But today we're going to talk about unlearned models. So when we have a model, we've done unlearning. You can check out what unlearning is. And then we attack that unlearning model. And so today we're going to say, when we unlearn something, when we take a model, we try to remove some information out of it, maybe memorized information, do we end up creating new artifacts that we can then attack and learn something that maybe we shouldn't know? Unfortunately, we have to start here, which is that Hayes et al., a really great paper about the fact that there's a lot of unlearning research out there that makes unlearning seem more effective than it is. And this is probably a mixture of cherry picking what to unlearn. So not unlearning a representative sample across the actual entire training data set, or not unlearning the complex examples as we learned about complex information is more useful and therefore gets stored more easily in the model, right? So how you choose the forget set matters in its representation compared to the other training data. And what these researchers found is that many of the unlearning papers that they reviewed had kind of either cherry-picked or by accident had a weaker sense. They also found that they used weaker attack methods to prove their insights. Now, this might be compute or time restraints or something like this, but the point is that the metrics that they found in many unlearning papers were not using the strongest attacks. So here we can see a baseline versus the LIRA, and we can see the LIRA is a stronger attack across all of them. And we can also see the dotted red line is a random guess. So for many of these papers, when they were evaluated by these researchers, A, they came up with different numbers. B, the strongest attacks, like a LIRA attack, was vastly different than what was published in the papers. So what do we learn? How you test your privacy leakage matters. Do you want to just get a paper that says you beat state of the art? Then you can cherry pick and do things. But if you want to do real research and contribute to the field, or if you're doing this for your company or organization, build out strong tests, right? That's what we need to do, because if we're actually trying to prove that we can protect things, then we should probably use strong testing, not weak testing. Okay. Another thing. So now we're moving into, we have an unlearned model, we have a learned model. So here we have original model, unlearned model to the left. Can we attack the unlearned model to learn something about what was unlearned, what was learned, something like this? And the answer is yes, we can. So particularly if we have the original model or access to the original model, this becomes much easier. But we could also have saved responses if we're talking about a black box attack where I don't actually see the activations inside the model because I don't have a copy of it. I just have the response from the service. If I have saved many responses before, and then the unlearning happens, new model version is released, and I compare what happened before to what happened after. If I have this over a representative enough sample, perhaps I can also see what was unlearned. Because if I have white box access, so if I can see the weights and I can see the activations, I can run it on my own computer, or I get the final two layers, so the logit layer of the model, then I can measure those. I can determine a hypothesis between this is the model before, this is the model after. And I might also be able to differentiate this is the data that it performs differently on before and after, which will, of course, then teach me something about what was unlearned or what was changed in the model behavior. Now, you've probably noticed this just in minor version updates of whatever AI vendor services you use. But if you're doing this intentionally over time, this indeed exposes a new attack method. And there's more links to the research in the blog posts in the description. And as you might imagine, if models are different, let's say just by only one example, we can actually reconstruct the gradient change between the model 1 and the model 2. You can think of this as you have a whole bunch of weights and biases, and you literally just overlap them and subtract, right? And then we get a directionality and a distance of the gradient changes on a node by node or network layer by network layer aspect. And unfortunately, or maybe fortunately, I don't know, that's enough information to teach us what information was removed. And so here's some examples from also another great paper where the Unlearned model was one example different, and these were the gradients that they were able to reconstruct from that. And I think it's an open research question, at what level of the amount of unlearned samples, particularly, let's say if there's a large batch of unlearned samples from one particular type of piece of information, how much could we then try to differentiate and make educated guesses about using these gradient differences about the information that was removed? That's very much, to some degree, an open research question. But if you are watching this and you work in research, I think there will be some interesting ways to attempt to find the biggest movers in these types of unlearning. But basically what we need to know is gradients can leak lots of information, and model differencing between two model versions can teach us things about gradients. And this is, of course, something that if we're unlearning at speed, like, every time a deletion request comes in, we're just running a quick unlearning and then new models out, this is definitely an attack that could surface. And then, unfortunately, there's an even bigger problem that we have that we kind of have to think about more holistically, and that's from a Carlini et al. Paper in 2022 called the privacy onion effect. And I want you to go back to thinking about the margin effect that we learned about earlier. I'll also link the blog post, which has the video in it and everything. But when we're thinking on some sort of projection space of, we have decision space here, we have input space here, and all of the layers in between are essentially some sort of projection space that's moving the information towards eventually that final decision space that it gets then projected into, and the decision is made in the model. And when we're thinking of this, what has been found is that the bigger the margins, the more robust the model. But what is also known is perhaps some of those margins, right? The space between two types of decisions, or the space between moving towards this type of decision versus that, or this next token versus that perhaps these examples on the edges, so to speak, are more at risk. So because they're at edge, right? This kind of makes sense. If you removed them, then the decision boundary wouldn't exist, right? Or it would exist somewhere else. And unfortunately, that's probably linked to memorization from what we understand now of the problem. And unfortunately, what happens is if we unlearn some, so let's take away these dots in space, these examples in space, and then we're training again. Okay, we're training again. Now we've actually moved the decision boundary. We've moved the margins, right? We've changed the margin. It's great. It's wider. So technically that tells us it should be more robust, presuming that our accuracy remains high. But now we got these other ones, right? And so this is exactly what this paper proved, is that if you remove the easiest points to attack, again, these are often going to be outliers or novel examples that are probably holding up a decision boundary, a critical one. You remove those. What happens? Well, now there's a new group that's holding up the decision boundary, right? And you can keep doing this, right? Until maybe you hit a huge cluster. This would be like the common examples. But then you can only generalize on things that are common, which is not often what we're doing in machine learning today. And so what the privacy onion effect tells us is that when we use unlearning to protect some data points, what we end up doing is actually exposing other data points. And that's why they called it the onion. So the first onion layer goes, then there's another, then there's another. Okay? So what does it mean? Well, But hopefully, one thing you've been learning is that thinking about unlearning is also thinking about learning. Okay, let me say that again. When we learn about unlearning or when we learn about memorization, we actually learn that learning itself might be different than we expected. Therefore, of course, unlearning is different than we expected. And this means that the privacy problem is much more complex than just removing and unlearning a few training examples. So, what I always encourage, first and foremost, is to talk interdisciplinarily. This means at your organization, you have product people talking with privacy people, talking with data engineering people. And if you don't have this, you need to practice this, because if you're not doing this, and I know everybody says, well, we're busy and we got this, that. Yeah, but the problem will not be addressed if we don't talk interdisciplinarily, because we can all have contributions we can make. And what I want you to talk about when you look at unlearning as a solution, does this actually fit what we're looking for? And do we have the capacity to do this correctly? Both from engineering resources, from a privacy, understanding the problem and setting some targets, right? And then also like testing and working on this within the product deadlines that we have. Understand and evaluate the risk and rewards. So here you heard about some new risks. So you need to be able to address those and understand, do they counteract the rewards that you think unlearning has? And make sure that you're building out testing and evaluations to actually do security and privacy as a normal part of your machine learning and AI workflows. And this means even if you're only using third-party AI endpoints, that's fine. But if you're not integrating security and privacy testing as a normal part of that workflow, then you can't decide model A is actually more secure or more private than model B, or how do we actually route these prompts based on what we think the privacy or security requirement for the response or something like this, right? These are all possibilities. These are all real things that people are doing in production systems, and you can too, okay? So I'd be curious to hear, what do you think about the unlearning risks, and do they counteract well with the rewards? And I'll see you soon for continuing to explore how we can address the problem of memorization. Next, we're going to dive into differential privacy. So stay tuned.